Hello, and welcome back. In sections 13.5 and 13.6, we're going to be investigating some common geometric objects in space. In section 13.5, we start with the two most basic of these, which are lines and planes in space. So our first goal is given a line in space, produce an equation that tells us any point on the line. So we have a couple questions to ask ourselves at the onset of this. Is what determines a line in space? How can I tell you, how can I sort of describe a line in space? And there's two answers to that. One, I could give you either 2 points that are on the line. So any 2 points in space or in the plane determine a line. Right, you simply draw a straight line between them, and now you have an entire line. And when we talk about lines, we are talking about sort of infinite, stretching infinitely. If we talk about a line segment, that's one that has a terminal point and an initial point. So 2 points can determine a line. We could also have 1 point and a direction. Now this one is going to turn out to actually be the most important way to think of a line, is a point somewhere that's on the line and then a direction to follow to get to any other point on the line. Because as it'll turn out, if we have 2 points on the line, we can recover a direction, and then we already have 1 point in the line. So this is going to be the most important way to think about a line: 1 point and a direction. So how we're going to do this is we're going to be given a line in space, and we'll have a fixed point that we know is on the line. So x naught, y naught, z naught. Think of this as a fixed point. So you can replace these with numbers, 1, 3, 5, for instance, something like that. Just a specific point that's on the line. So this is specific. And then we'll have a vector parallel to the line. So this is going to be our direction vector. Direction vector. So this tells us our point that's on the line, and this tells us which way to move. We'd like to take these two things, a point and a direction vector, and spit out an equation of the line. Now another thing to get at here is that there's 2 ways of us expressing that line, or at least 2 ways we're gonna think about, and that is in a vector equation. So we'll see x, y, z, that vector, equal to some function of a variable t, or as a parametric equation. So the point x, y, z equal some function of t for the x coordinate, some function of t for the y coordinate, some function of t for the z coordinate. Here we'll have functions of t for each of the components. So there'll be an easy way of going back and forth between these 2 things, but we'd like to be able to do both because both have their purposes. So how I'm going to start this discussion here is I'm just going to do this in 2 dimensions. I'm going to work with 2 dimensions and show you how we can get an equation of a line given a point and a vector parallel to the line. And actually, I'm going to start with 2 points that are on the line. So here's my example I have here. Here's my line L, and again, I'm just in 2 dimensions here. Again, in 2 dimensions or in 3 dimensions, any 2 points will determine a line. So this will actually work pretty well for our purposes, just to reduce down to 2 dimensions. So P naught, think of this like my fixed point on the line. P1 is just some other point on the line that I know. But P naught I'm going to really focus on here. We could use P1 as P naught. It doesn't really matter. As long as I have a fixed point that I'm sort of determining, I'm going to say this is just going to be fixed. And what I can do here is I can form the vector. I'll just freehand it. I can form the vector, the position vector for P naught. So this is going to be the vector -3, 2. That's my position vector. I'm going to call this R naught. So this vector, position vector, points to my fixed point on the line. Now, here's where it gets really cool. I also need a direction. If I can have a direction, if I can figure out the direction of this line, it'll be easy to recover the equation. So how can I find a vector in the direction of this line? So a vector that's parallel to this line. So let me say here, vector parallel to L. Well, if I have 2 points on the line, then I can form the vector between them. So I'm talking here about, I'll use blue for this, I'm talking here about this vector, P0 to P1. So let's find P0, P1. Again, this is if I have 2 points on the line. We can talk more in a bit about what if I don't have another point on the line and I just have a direction vector. That's okay. Again, this is getting our direction vector, which I'm going to call V. Call that one V, direction vector. And in this case, where I actually have numbers, I can work out exactly what that is just so we can play around with this example. So from P0 to P1, looks like I have to go in the X direction 5, up 5, and up, so over 5 and up 2. So my direction vector here is 5, 2. And if I just plot that, so here's 1, 2, 3, 4, 5, 2. Here is that vector again, V. Here's my direction vector, V, just in a different location. But remember, it doesn't matter where I write these things. This is V. This is also V. Okay, so cool. So now we have a direction vector. And what can I do with this? Well, what I can do is I can add, let's see what happens when I add R0 and V. So let's see, what do I get if I take R0 and add V to it? I wanted to do that in multiple colors, sorry. Let's do V in blue there. R0 and V. And what do we get out of this? Well, R0 is negative 3, 2. So this will be negative 3, 2 plus 5, 2. And that gives us what? 2, 4. Which is my position vector for P1. So I'm going to go ahead and put that in, let's use like this light blue for this one. So this vector R0 plus V is this vector here. So I'm going to call that, I'll call that, how about R1? I'll call that R1 here. And notice that R1 points, its head is on the line. So head of R1 is on L. Okay, so all right, that's maybe you don't think we did a whole lot there, but actually we're very close to having the vector equation of this line. So what if instead of just adding V, I add a scalar multiple of V? So let's say I add, I don't know, how about 2V to this? So maybe I'll call that R2. And I'll do, so my fixed point on the line, R0, plus, let's add 2 V0. So maybe I'll use a different color for that, 2. Oops, I don't like that at all. Let's just use white for the scalar multiple. 2 V. So let's add 2V to this. And let's see, what do we get now? So if I add 2V to this, so V goes this way, 2V is going to be over 10 and up to 4, so it's going to be something like this. So it's going to go over 10 and up 4, so I should be at 7. 7 over 10, up 4, up to 6. So I need to go one more here. So that'll happen. Oh, what do you know? So let me draw that one again. That's going to be R2. I'll just freehand that. So there's my R2 vector, which again points on the line. Again, remember how vector addition works. If I add R0 and V, then I go from tail of R0 to the head of V, and that'll be on the line. And let's see if I do 2V. So 2V was this one. There's 2V. And again, it's on the line because V is parallel to the line. Let's see what happens. So what did this actually give us? I don't really care too much what exactly R2 is. What was this? This was 7, 6. But what if I went, say, in the other direction? What if I want these parts of the line? So what if I did, let's say, I'm going to call this r -1. Going a little bit off book in terms of notation here, just to illustrate a point. So again, I'm going to take r naught, my special vector that points to the line, plus, and this time we'll do -1 times my vector v. So now my direction vector v is going to point in the opposite direction. So rather than being 5, 2, it's going to be -5, -2. So that's down here. And notice that it goes in exactly the opposite direction as we've discussed before. Multiplying a vector by a negative scalar switches the direction, makes it the opposite direction. So this would be then -v, and that's going to come down from p naught like this. Let's see, what was -v? -v would be -5, -2. So this should be at -8, 0, and that's right here. And so my r -1 will point to this point on the line. So what I'm trying to illustrate here, and I'm not going to worry figuring this out, whatever. What I'm trying to illustrate here is that if I do r naught plus any scalar multiple of v, then that will ensure that that sum, r naught plus the scalar multiple of v, will be on the line. It'll be some point on the line. So if I consider r naught plus any scalar multiple of v, I get any point on the line. And that's exactly what an equation of a line needs to be. It needs to be able to tell me any point on the line. So let me write here so r naught plus any scalar multiple of v is on the line. And even more so, this goes in the other direction. Any point on the line looks like r naught plus some specific scalar multiple of v. And so we'll let p, so let me maybe jump over here again. So we need a variable point on the line. So what I'm going to say here is, here's our line in space. Here's our fixed point. We have a direction vector, which we got over there by taking the direction between the 2 points. And then we'll let p, x, y, z be a variable point on the line. And we want our vector r to give us any point on the line. OP will be any variable point on the line. So what is my vector r? So r could be over here, r could be here, r could be here. R is going to change. R is variable. So I'm going to say here, r, this vector is variable point on L. And by this here tells me that r has the form r naught plus some scalar multiple of v. So r is equal to r naught plus some scalar multiple of v, or any scalar multiple of v. And so here I introduce a parameter t, which will take any real number between -infinity and infinity. So t, that's a scalar, times my direction vector v. A direction vector v, again, in this case, when we had 2 points, came from the vector between the 2 points. So in this case, what is r in this case, my variable point on the line? This will be my r naught, which was -3, 2, plus any scalar multiple, so t, times my direction vector, which was 5, 2. And so this is a function of t. So I really should say here, we're now having vectors which are functions of parameters, t. So here we're saying t is what's called a parameter. And you should have dealt with these before in Calc 2 with parametric equations. We're going to get to parametric equations in just a second here in this video. So this works for my equation of the line, equation of L, and we call this a vector equation because I have a vector which depends on my parameter t, and I have an expression that churns out any vector on the line right here. So this works brilliantly. This is my vector equation of the line L. Now, the other thing I can do here is combine these. I could also say r of t is equal to, I could actually add these vectors. I can bring the t through since it's a scalar multiple and add these. So I'll do that in 2 steps here. Negative 3, 2 plus 5t, 2t. And then I can actually add those vectors. So this looks like negative 3 plus 5t and 2 plus 2t. And honestly, this should look familiar because in each component, I have an equation of a line with respect to t. So that is, if this is my x component, it's some function of t, and my y component is also a function of t. So that tells me there's another way to express this vector equation. I can also give you parametric equations. I can tell you how to get the x value and how to get the y value. So the other way to think about this is parametric equations for the line. So parametric equation for L. So that, remember, consists of an equation for each component. So my parametric equation would be this: x of t is equal to negative 3 plus 5t, and y of t is equal to 2 plus 2t. So hopefully this is sort of refreshing your memory of parametric equations that you should have encountered in Calc 2 and be somewhat familiar with. So here is 2 ways to represent this line L, one with a vector equation. You could give, the vector equation could also be given as this thing, or as a set of parametric equations for the line. All right, so that's 2 dimensions, but I'll tell you what, it really doesn't change much for 3 dimensions. So what I'm going to do is I'm going to jump to an example in the text, in the e-text, this one, just to show you how this works in 3 dimensions. It's a little bit easier for me to do this in Mathematica, in the e-text. So I'll do that. So here I have my fixed point on the line, P naught. And I can change that. I do encourage you to play around with this applet here in the book, but I'm just going to stick with the presets. So there's my point on the line, and I have a vector pointing to it. That's my r naught. And then I have a direction vector v. And again, vector addition works the same in 3 dimensions as it does in 2 dimensions. If I do r naught plus any multiple of v, I get another point on the line. So I can change my t value here. I can make it 2v, or I can do 3v, is going to be further along down the line. I can do negative values. That's going to push it this way. I'll change it so I can see that stuff. Sometimes it's a little hard to see this stuff. But that'll give me a point over there on that side of the line. And I can go even farther that way if I want, or I can input 0 for t. That'll give me my p naught. And again, any multiple of v will give me a point on the line. So it's working exactly the same way as it does in 2 dimensions. All I need is a point on the line and a direction vector, and I can recover a vector equation for it. So let's just jump back to this for a second and look at what the equation looks like in 3 dimensions. It's going to look the same as this, but just extended to vectors with 3 components. So the line L is the set of all points in the head of the vectors x, y, z. So again, we have direction vector v, so p naught is a fixed point. And let's say its p naught is x naught, y naught, z naught. And then we have a direction vector v. So let's say direction vector. Again, if I need to obtain this direction vector, I can do that if I have 2 points on the line. Again, I can take the vector between the 2 points that are on the line. That gives me a direction vector that will work. And so the direction vector, I'm going to call this A, B, C. So that means if my fixed point is this, my r naught, the vector that points to that fixed point, is just going to look like x naught, y naught, z naught. And then the equation of my line is going to be, so x, y, z, and let me call this, how about r of t? I'm going to get rid of this, actually. Is going to look like my fixed vector, x naught, y naught, z naught, plus any scalar multiple of t. So t times a, b, c is my direction vector. And so another form of that, right, I can actually combine these. Looks like x naught plus at, y naught plus bt, z naught plus ct. Now the other thing I need to do, if you remember from parametric equations, I need to tell you what values of t should be considered. So for an infinite line like we're doing right now, a line that extends infinitely in both directions, we just let t go from negative infinity to positive infinity, exclusive on the infinities. I'll say here where that happens. And so this is our general equation of the line. The line L, if I want to give the parametric equations for the line, I just grab the components of this. So my x of t will be x naught plus at. My y equation will be y naught plus at. And my z equation will be z of t, z naught plus ct. I did make a mistake here. This should be bt. And there's my parametric equations for the line. Okay, so that's the end of this video. I'll have a few example videos where we'll find equations of lines, and then we'll eventually graduate to talking about equations of planes, where the cross product will be quite useful. All right, I'll see you there. Thanks for sticking around.